Hello everyone, my name is Naina and I am from the Buddhi Academy. So today we will see about the redox reactions. In today's part we will basically focus on oxidation number and types of redox reactions. There are 4 types of redox reaction: combination, decomposition, displacement and disproportion reaction. We will see each in detail. So let's start with the oxidation number. So a less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction. So oxidation, we have learned in our previous video about oxidation and reduction with respect to hydrogen, with respect to oxygen and with respect to electrons also. Now oxidation number, a less obvious example for electron transfer, okay, how electrons are transferred, is realized when we combine hydrogen with oxygen to form water, where 2 hydrogen or 4 hydrogen molecules are involved and 4 hydrogen molecules and 2 oxygen molecules are involved to form 2 moles of water. Though not simple in its approach, yet we can visualize the hydrogen atoms as going from a neutral, that is 0 state in H2 to a positive state in H2O. The oxygen atom goes from a 0 state in O2 to a di-negative state in H2O. So here, even though we cannot make out, but it is clearly seen that hydrogen and oxygen both are in their neutral form. So when they are converted to water molecule, hydrogen from a neutral 0 state, it goes to a positive state. So hydrogen from a neutral 0 state, it turns to a positive state in H2, whereas oxygen from atom again from its 0 state in O2 to a di-negative state in water molecule. Now it is assumed that there is an electron transfer from hydrogen to oxygen and consequently H2 is oxidized and O2 is reduced. So it is assumed that when there is a formation of water, there is transfer of electrons which are seen from hydrogen to oxygen, whereby resulting in the oxidation of hydrogen and reduction of oxygen. Now, however, as we see later, the charge transfer is only partial and it perhaps better described as an electron shift rather than a complete loss of electron by hydrogen and gain by oxygen. So however, the water molecule is neutral, so it is seen that there is a partial transfer which has taken place. We cannot say it is a transfer, it is just an electron shift. Rather than saying partial electron transfer, we can say an electron shift that has taken place, not loss of electron by hydrogen and gain of electron by oxygen. Now, what has been said here with respect may be true for a good number of other reactions involving covalent compounds. So whatever happens with water molecule, it can also be seen in some of the other reactions involving covalent compounds. 2 such examples are hydrogen chloride, that is your HCl, and CCl4, carbon tetrachloride, which is formed. In these 2 cases also same thing happens what had happened with hydrogen and oxygen. There is no loss or gain of electron, it is just electron shift that is taking place. Now, in order to keep track of electron shifts in chemical reactions involving formation of covalent compounds, a more practical method of using oxidation number has been developed. Now, if there is an electron transfer, we can directly say that this particular atom has lost 1 electron and this particular atom has gained 1 electron. But here, there is no transfer as such is occurring. It is only an electron shift that is seen. So in that case, to explain or to keep a track of such electron shifts, this concept has been put forward of using oxidation number. Okay, so in this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. So in this case, it's always assumed that there is a complete transfer, okay, from electron, complete transfer of electron from a less electronegative atom to a more electronegative atom. For example, we rewrite the equations to show charges on the each atom. Here we have written a simple reaction. Now we will write a reaction where we show charges on each of them. Hydrogen, as I already explained here, initially it was with zero charge, oxygen also with zero charge, but as both of them combine and form a water molecule, it is seen that hydrogen has a positive charge whereas oxygen has a di-negative charge, -2. Okay, similarly for other two molecules also, initially they were zero, but as they combined to form a molecule, they each got a charge of plus and -1. Okay, similar with other molecules. It may be emphasized that the assumption of electron transfer is made for bookkeeping purpose only, and it will become obvious at later stages in this, until that it leads to the simple description of redox reaction. So here oxidation number or the assumption of electron transfer, it is made for bookkeeping purpose. Okay, it will become very obvious at a later stage. Now again, oxidation number, it denotes the oxidation state of an element in a compound ascertained according to a set of rules formulated on the basis that electron pair in a covalent bond belongs entirely to more electronegative element. So oxidation number, what basically it denotes the oxidation state of an element in a compound which is ascertained according to a set of rules formulated on the basis of electron pair in a covalent bond that belongs entirely to more electronegative elements. So there is a set of rules which are made to formulate the basis of electron pairs in a covalent bond that belongs entirely to the more electronegative element. It is not always possible to remember or make out easily in a compound or ion which element is more electronegative than the other. As you know, here they have said it depends more, or it entirely belongs to the electronegative element, but for some molecules it is always not possible to remember or to predict which of them are more electronegative. So therefore a set of rules has been formulated, okay, to determine the oxidation number of an element in a compound or ion. So rather than remembering their valence shells, valence electrons, what will be the oxidation state, you cannot directly predict. So to determine the oxidation number, an element or a compound of ion, a set of rules has been given. If two or more than two atoms of an element are present in the molecule, okay, or ion, such as Na2S2O3 or Cr2O7, the oxidation number of atoms of that element will be the average of the oxidation number of all the atoms in the element. If there is only single atom, whatever oxidation number is there, that is the oxidation number of that atom. But when there is more than two atoms or polyatomic molecule is present, here sodium is there, sulfur is there, oxygen is there, so there is a polyatomic, no? In this case, the average oxidation number, average of the oxidation number is taken as the oxidation number of the molecule. So adding all the oxidation states and dividing it by the number of atoms, you get an average oxidation state. So that is considered to be the oxidation number of that molecule. We may at this stage state the rules for calculation of the oxidation number. So let us see the rules that are put forth for calculating the oxidation number. The first rule is, in elements, okay, in the free or the uncombined state, each atom bears the oxidation number of 0. So an element, Okay, when element is present in free or uncombined state, when they are present uncombined solely for themselves, that time the oxidation number is considered to be 0. Okay, for example, H2O2, Cl2O, 3P4, even within themselves they can form bonds, but with other molecules involvement, okay, they have a oxidation number of 0. Second rule, for ions composed of only one atom, the oxidation number is equal to the charge on the ion. Thus, Na plus ion has an oxidation number of +1, Mg2 plus ion has +2. So when an ion, okay, when an ion is present in a free state, okay, so in that case, whatever charge it has, that charge will be its oxidation number. For example, Na plus will have +1 charge, Mg2 plus will have +2 charge, Fe3 plus will have +3 charge. Okay, when an ion is present in its free or one atom state, the oxidation number is equal to the charge on the ion. Now, in their compounds, all alkali metals have oxidation number of +1 and all alkaline earth metals have an oxidation number of +2. So, with respect to this, when there is ion formed of alkali metals, or the alkali metals and alkaline earth metals are S block elements. Okay, first two columns of the S block. So first one is the alkaline metals and second one is the alkaline earth metals. For alkaline metals it is +1 oxidation for always, and for alkaline earth metals it is +2. So aluminium is regarded as an oxidation number of +3 in all its compounds. So aluminium has an oxidation number of +3 in all its compounds. Now, third rule, the oxidation number of oxygen in most compounds is -2. However, we come across two kinds of exceptions here. One arises in the case of peroxides and superperoxides, the compound of oxygen in which oxygen atoms are directly linked to each other. So, in most of the cases, we see oxygen has an oxidation number of -2. However, there are two kinds of exception which is seen. One which arises in case of peroxides and superperoxides, or superoxides, peroxides and superoxides. In this case, oxygen atoms, they are directly linked to each other. Okay, while in peroxides, H2O2 or Na2O2, each oxygen atom is assigned an oxidation number of -1. In superoxides, that is KO2 and RbO2, each oxygen atom is assigned an oxidation number of -12. Even though oxygen shows an oxidation number of -2, but in peroxides and superoxides, okay, in both these cases, oxygen show oxidation state of -1 and -12 respectively. This is the first exception. Second exception appears rarely. This is common. Okay, peroxides and peroxides and superoxides, we see them commonly. So these are common exceptions. Second exception is very rare. Okay, it appears rarely when oxygen is bounded to fluorine. So whenever oxygen is bounded to fluorine, such as oxygen difluoride OF2 or dioxygen difluoride O2F2. Okay, the oxygen is assigned an oxidation number of +2 and +1. Instead of a negative sign, it gets a positive sign, because compared to oxygen, fluorine is more electronegative. Okay, so oxygen gets a positive sign. So the number assigned to oxygen will depend upon the bonding state of oxygen, but this number would now be a positive figure only. Okay. So we have seen exceptions for oxygen. First one is in peroxides and superoxides, where peroxide oxygen, when it is present in a peroxide form, it shows a -1 oxidation state. When it is present in superoxide form, it shows a -half oxidation state or oxidation number. Whereas the second exception is rarely seen, where oxygen is bonded with fluorine. Okay, in that case, oxygen shows a positive oxidation state or oxidation number. This is basically because of the electronegativity of fluorine. Next one is the oxidation number of hydrogen is +1 except when it is bonded to metals in binary compound, that is compounds containing two elements. For example, LiH, NaH and CaH2, its oxidation number is -1. So now the oxidation number of hydrogen is always +1. Oxidation hydrogen always shows a +1 oxidation state, except when it is bonded to a metals in binary compounds. Okay, binary compounds mean compounds containing two elements. For example, lithium hydride, sodium hydride, calcium dihydride. In these scenarios, its oxidation number is -1. Okay. Now, in all its compounds, fluorine has an oxidation number of -1 or -1. Fluorine, it always shows a -1 oxidation number. Other halogens like chlorine, bromine and iodine also have an oxidation number of -1. Basically all the halogens, they show a oxidation number of -1 when they occur as halide ions. Okay, when they are present in halide ion forms, they show a oxidation state of -1. Chlorine, bromine and iodine, when combined with oxygen, for example oxoacids and oxoanions, have positive oxidation numbers. Okay, here also there is an exception. When chlorine, bromine and iodine are involved with oxygen in the formation of oxoacids and oxoanions, they show a positive oxidation number. Okay, now last rule is that the algebraic sum of the oxidation number of all the atoms in a compound must be 0. So overall, when there is a reaction that takes place, okay, the entire net charge or the net oxidation number, sum of the oxidation number of all atoms in a compound must be 0. It should always have a 0 value when you calculate it. Okay, in polyatomic ions, the algebraic sum of all the oxidation number of atoms of the ions must equal the charge on the ion. So in polyatomic ions, the algebraic sum, okay, of all the oxidation numbers of atoms of the ion must equal to the charge on the ion. Thus, the sum of oxidation number of 3 oxygen atoms and 1 carbon atom in the carbonate ion must equal to -2. So in short, whenever you calculate the overall net oxidation state of the molecule, you should get a answer to be 0. Both the oxidation state, when you combine them, you should get the net oxidation state. By the application of above rules, we can find out the oxidation number of the desired element in a molecule or in an ion. So by applying all these rules, we can find out the oxidation number desired for the element that we are looking into. Now, it is clear that the metallic elements have positive oxidation number, and non-metallic ions have a positive or a negative oxidation number. So with these rules, we can clearly state that metallic ions, okay, metallic elements, they have a positive oxidation number, whereas non-metallic elements, they have a positive or a negative oxidation number. Now, the atom of transition elements usually display several positive oxidation state. Transition metals, they show several positive oxidation states. Several means from +2 to +7 oxidation states can be seen in transition elements. Now, the highest oxidation number of representative element in the group number for the first two groups of the and the group number -10 following the long form of periodic table for the groups. Now, if you want to find out the highest oxidation number of a representative element in element is the group number, okay, for the first two groups and the group number -10 following the long form of periodic table. Now, for the groups, you have to subtract first two groups, and for the long term, we have to subtract the group number -10 for the other groups. Thus, it implies that the highest value of oxidation number exhibited by an atom of an element generally increases across the period and periodic table. In the third period, the highest value of oxidation number is 1 to 7. So if according to this, it implies that the highest value of oxidation number exhibited by an element, it generally increases across the period as we go from left to right. So, and for third period, the highest value of oxidation number is 7. Okay, indicated below in the compounds of elements. Now, a term that is often used interchangeably with the oxidation number is the oxidation state. Okay, as I was talking now, I was getting both the terms involved, right? Oxidation number and oxidation state. Thus, in carbon dioxide, the oxidation state of carbon is +4, and that is also its oxidation number. So oxidation state and oxidation number is almost same. For example, in carbon dioxide, the oxidation state of carbon is +4, and the oxidation number of carbon in carbon dioxide is also +4. Now, similarly, the oxidation state of as well as oxidation number of oxygen is -2 in carbon dioxide. Now, this implies that the oxidation number denotes the oxidation state of an element in a compound. Okay, since both oxidation state and oxidation element both are similar, they correspond to each other. Now, the oxidation number or state of a metal in a compound is sometimes presented according to the notation given by German chemist Alfred Stock. Okay, so sometimes the oxidation number or state of a metal in a compound we represent or present it according to the German chemist Alfred Stock. It is popularly known as Stock notation. Okay, so that notation is known as Stock notation. According to this, the oxidation number is expressed by putting a Roman number representing the oxidation number in parenthesis after the symbol of the metal is metal in the molecular formula. So whenever you write a molecular formula, after the molecular formula, the oxidation number of that particular element is shown in the Roman numbers. Okay, now, thus Aurous chloride and auric chloride are written as Aurous and auric chloride, gold. Okay, gold, AU is for gold. We call it Aurous chloride and auric chloride, not gold chloride and gold chloride. So it is Aurous chloride and auric chloride. We can show in Aurous chloride it is AU, the oxidation state of AU is 1, and in auric chloride it is 3. Similarly, stannous chloride and stannic chloride, same thing. Stannous, the oxidation number is 2 for stannum, and in stannic chloride it is 4. So this change in oxidation number implies change in oxidation state, which in turn helps to identify whether the species is present in oxidized form or reduced form. So there is a change which is seen, right? Once they have an oxidation number of 1, other same element is having another oxidation state, that is 3. Again 2 and 4. Now this change or variation in oxidation number, it helps us to identify whether the species present is in oxidized form or reduced form. Thus Hg21Cl2 is reduced form, and Hg2Cl2 reduced form of Hg2Cl2. So this is a reduced form of this. So it basically helps us to explain who is reduced and who is oxidized. Now the idea of oxidation number has been invariably applied to define oxidation, reduction, oxidizing agent, reducing agent, and redox reaction. So this oxidation number, it is applied to define the reduction, oxidation, oxidizing agent, reducing agent, and redox reaction. Now let's see how. Just a summary here. So oxidation, an increase in the oxidation number of element in the given substance. So with respect to oxidation number, the definition of oxidation is there is an increase in oxidation number of an element. Okay, reduction means a decrease in oxidation number of an element in a given substance. Now what is oxidizing agent? A reagent which can increase the oxidation number of an element in a given substance. When that element can increase the oxidation number, that is called as oxidizing agent. The reagent is called as oxidants. Reducing means a reagent which lowers the oxidation number of an element in a given substance. Now these reagents are called reductants. Okay, so redox reaction which involves change in oxidation number of the interacting species. Okay, next is the type of reactions, redox reactions. When we say type of redox reactions, as I told you in the beginning, we have 4 types of redox reactions: combination, decomposition, displacement, and disproportionation. What is combination reaction? A combination reaction may be denoted in the manner A plus B gives you C. Both A and B is combining together to give you a product is C. So either A or B, either A and B or both A and B must be in the elemental form for such a reaction to be a redox reaction. So either one of them should be in an elemental form so that redox reaction can take place. Now all combustion reactions which make use of elemental dioxygen as well as the other reaction involving elements are other than dioxygen are redox reactions. So when we use elemental dioxygen or other elements involving other elements other than dioxygen are redox reactions. Some important reactions are carbon and oxygen. Both are present in their neutral state. After combining, they form +4 and -2 oxidation states. So these are combustion reaction or combination reaction. Here reaction along with reaction, these representations are also very important. You have to show the representation from which state they are transferring to which state. Okay. Next is decomposition reaction. Decomposition reaction are the opposite to combination reaction. Combination reaction means you are combining two things to form a third thing. Here you are breaking one component into two or more different components. So precisely a decomposition reaction leads to breakdown of compound into two or more components, at least one of which must be in the elemental state. So here what you have to consider is here the reaction in decomposition, it breaks down a compound into two or more components. Here at least one should be present in the elemental state to be broken down into its to get that redox reaction. Okay, for example, water molecule. Again you get a elemental components. Okay, it may carefully to be noted that there is no change in the oxidation number of hydrogen in methane under combination reaction, and that of potassium in potassium chlorate reaction. This may also be noted here that all decomposition reactions are not redox reactions. Okay, in the combination reaction here methane is used. Yes or no, methane is decomposed, but you can see the hydrogen. Here also it was having +1 charge, here also it is having a +1 charge. So hydrogen is not involved in the methane reaction. And in case of potassium chlorate, here again potassium is in +1 state, again here also it is in +1 state. So in both these reactions hydrogen and potassium are not involved in the reaction. This may also be noted here that all decomposition reaction are not redox reaction. For example, decomposition of calcium carbonate is not redox reaction. So here main thing that you have to note is not all the decomposition reactions can be compared with the redox reaction. There are some reactions which doesn't follow the decomposition pattern. Now displacement reaction. In a displacement reaction, an ion or an atom in a compound is replaced by an ion or an atom of another element. It may be denoted as here displacement. You replaces the or you exchange the molecules with each other. For example, X plus YZ. So Y from Y this Z is taken by X. So it became XZ plus Y. Okay, so displacement reaction fit into two categories: metal displacement and non-metal displacement. So for displacement reaction there are two categories: metal displacement and non-metal displacement. Let's start with metal displacement. A metal in a compound can be displaced by another metal in the uncombined state. So when there is a combined metal form, it can be displaced by another metal in the uncombined state. So one should be combined, other should be uncombined. So for example here, copper sulfate, copper is also a metal, zinc is also a metal. In copper sulfate, copper is combined with sulfate and zinc is non-combined. Later, zinc replaces copper and becomes zinc sulfate. So we have already discussed about this. So metal displacement reaction find many applications in the metallurgical processes in which pure metals are obtained from their compounds in ores. So where this metal displacement is used, it is basically used in metallurgical processes where you can isolate pure metals from their ores. Okay, some of the examples are given here. As I explained here that copper is displaced by zinc. Okay, some other examples is also given here. So in each case the reducing metal is a better reducing agent than that one that is being reduced, which evidently shows more capability to lose electrons as compared to the one that is reduced. So here the metal which is reducing, okay, so here which metal is reducing? Copper is reduced, zinc is reduced from zinc original state to zinc 2 plus. So the ones which is reducing, okay, the metal which is reducing is a better reducing agent than the one which is being reduced, okay, which shows more capability to lose electrons as compared to the one that is reduced. The next one is non-metal displacement. Now we have seen metal displacement. Next one is non-metal displacement. So the non-metal displacement redox reaction include hydrogen displacement and rarely occurring reactions involving oxygen displacement. So in non-metal displacement, it is basically the hydrogen displacement and rarely occurring oxygen displacement. So all alkali metals and some alkaline earth metals are involved in this process, which are very good reductants, will displace hydrogen from cold water. Okay, here they replace hydrogen from the water molecules. Okay, sodium and calcium. Less active metals such as magnesium and iron react with the steam to produce dihydrogen gas. Okay, here also, now in this case the cold water is used, okay, for sodium and calcium, whereas for magnesium and iron steam is used. When steam is produced and magnesium and iron are reacted with this steam, they produces dihydrogen gas. So many metals, including those which do not react with cold water, are capable of displacing hydrogens from acid. So many metals, okay, including those, okay, which do not react with cold water, like sodium and calcium, they are capable of displacing hydrogens from acids. Okay, so dihydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. A few examples for the displacement of hydrogen from acids are zinc, HCl, zinc chloride and H2. So dihydrogen forms acids. Okay, many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Now dihydrogen from acid may even be produced by such metals which do not react with steam. Okay, there are two examples I have given you. One which reacts with cold water, other which reacts with steam. Now, the metals which doesn't react with cold water can displace the hydrogen from acids. Now the ones which produces such metals do not react with steam. Okay, cadmium and tin are the examples of such metals which can react with acid, which can displace hydrogen from acid, but they cannot react with cold water nor with the steam. Okay. Now, basically these reactions are used in the laboratories for the preparation of hydrogen gas. Now here the reactivity of metal is reflected in the rate of hydrogen gas evolution, which is the slowest for the least active metal Fe. So the reactivity of metal is reflected in the rate of hydrogen gas evolution. So whoever evolves the hydrogen gas in a faster way, the reactivity is more. In slower way, the reactivity is less. So in this case, the slowest for the least active metal Fe and the fastest for the most reactive metal Mg. So magnesium is the most reactive metal because it produces hydrogen gas more frequently than iron, which is less reactive. Now very less reactive metals which may occur in the native state, such as silver and gold, do not react even with hydrochloric acid. There are very less metals which may occur in the native state, such as silver and gold. So they do not react with hydrochloric acid. Now we have already discussed that the metals like zinc, copper and silver, through tendency to lose electron, show they are reducing activity in the order of Zn is having more tendency to release electron than copper than silver. Right? This was what we discussed in our previous video. Like metals, activity series also exist for the halogens. The power of these elements as oxidizing agent decreases as we move down from fluorine to iodine in group 17 of the periodic table. So like this, there is a series which exists for the halogens. The power of these elements, oxidizing agents, decreases as we move from fluorine to iodine in group 17 of the periodic table. This implies that fluorine is so reactive that it can replace chloride, bromide and iodide ions in solution. Now in fact, fluorine is so reactive that it attacks water and displaces the oxygen of water. Okay, so this implies from fluorine to iodine it decreases. So fluorine is more reactive. So in that case, the reactivity that it can replace chlorine, bromide and iodine in a solution. So fluorine can replace the other molecules in its subsequent group. So in fact, fluorine is also reactive that it attacks water and displaces oxygen for water from the water. So from the water molecule, fluorine can replace the oxygen and form an HF bond. Now it is for this reaction that the displacement reaction of chlorine, bromine and iodine using fluorine are not generally carried out in the aqueous solution. Now, because of this reason, when you want to replace or displace chlorine, bromine or iodine using fluorine, you cannot carry out that experiment with respect with aqueous solution with water, because fluorine, other than replacing chlorine, bromine and iodine, it can also replace oxygen from the water molecule. So in other hand, chlorine can displace bromide and iodine ions in an aqueous solution. So in that place, chlorine, it can displace bromine and iodine. Okay. Now, as bromine and iodine are colored and dissolved in CCl4, can easily be identified from the color of the solution. So bromine and iodine, since they are colored, bromine is brown in color, iodine is also in yellowish orange in color. So when you dissolve it in CCl4, you can easily identify the color of the solution. Okay, so this is the above reactions. Okay. In detail, what happens when we replace the chlorine and bromine iodine or chlorine and bromine with each other. Now, from the basis of identifying bromine and iodine in the laboratory through the test popularity known as layer test. Okay, so you can identify bromine and iodine in the laboratory. Both of them are having similar color, but you can identify them by a layer test. It may not be out of place to mention here that bromine likewise can displace iodine ions. So even though chlorine can replace bromine and iodine, it is also possible that bromine can replace iodine. Okay, so eventually it will be like they will interchange their oxidation state. Now, the halogen displacement reactions have a direct industrial application. The recovery of halogens from their halide requires an oxidation process. Okay, so halogen displacement reaction, it is directly involved with the industrial application, or it is directly used for industrial application, and recovery of halogens from halides can also be done using oxidation process. Here X denotes the halogen atom, so this X denotes the halogen element, whereas chemical means are available to oxidize chlorine, bromine and iodine, as a fluorine is the strongest oxidizing agent. So there are other chemical means which are available to oxidize chlorine, bromine and iodine. For fluorine, it is the strongest oxidizing agent. This you have to remember. Fluorine is the strongest oxidizing agent. There is no way to convert fluorine ion to F2 by chemical means. Now the only way to achieve F2 from F minus is to oxidize electrolytically, the details of which you will study in your later stages. So you cannot convert fluorine ions into fluorine molecule, but you can convert fluorine molecule into fluorine ion if you oxidize it electrolytically. Okay, the detail of that you will learn in your later classes. Next is the last reaction, that is the disproportionation reaction. Now disproportionation reaction are a special type of redox reaction. Okay, in a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. So in disproportionation, what happens? Element in one oxidation state, it is simultaneously oxidized and reduced. One of the reacting substance in a disproportionation reaction always contains an element that can exist in at least 3 oxidation states. So in this reaction, you have to use an element which can exist in at least 3 oxidation states. It should have 3 oxidation states to it. The element in the form of reacting substance, it is in the intermediate oxidation state, and both higher and lower oxidation states of the element are formed in the reaction. So if it has 3 oxidation state, okay, in a reaction the higher and the lower oxidation states are formed, okay, and the reacting substance is kept in the intermediate oxidation state. Now the decomposition of hydrogen peroxide is a familiar example of the reaction where oxygen experiences disproportionation. So the example here is hydrogen peroxide where oxygen experiences disproportionation. How? Now H2O2 both are present in +1 and -1 oxidation state. We will focus on oxygen because oxygen is the one which experiences the disproportionation. So oxygen initially in hydrogen peroxide form, it is present in -1 charge. So when you split it, okay, when decomposition takes place, oxygen acquires a -2 charge, okay, and a 0 oxidation state. The one which is associated with water has a -2 charge and the one which is released has a neutral state. Here the oxygen of peroxide which is present in -1 state is converted to 0 oxidation state in O2 and decreases to -2 oxidation state in water. Okay, so it was initially when it was combining it was 0, when it combined it became -1, and when it dissociated it became -2. So it shows 3 oxidation state variations. This is the disproportionation reaction. Now phosphorus, sulfur and chlorine undergo disproportionation in alkaline medium. So phosphorus, sulfur and chlorine, they undergo disproportionation in alkaline medium. Alkaline medium means when there is presence of OH. Okay, they show a disproportionation reaction. Here phosphorus is in 0 state. Later in the product it became -3 and +1. So it showed 3 oxidation state. One with 0, one with +1 and one with -3. Okay, similar for sulfur and chlorine. Initially they were with 0 oxidation state, but when they were converted into products, they are having -2, +2, -1 and +1 oxidation state respectively. So this is the disproportionation. They show various oxidation states in one reaction. Now the reaction describes the formation of household bleaching agents. Now this reaction is basically the formation of household bleaching agent. Okay, you know we put bleaching powder, right? That is hypochlorite ion. Formed in the reaction oxidizes the color bearing stains of the substances to colorless compound, and this hypochlorite, it bleaches the color bearing stains. Even we use it for clothes also, to remove the stains, right? So it removes the color bearing stain to colorless compounds. Now it is of interest to mention here that whereas bromine and iodine follow the same trend and exhibit the chlorine reaction. So for other than chlorine, bromine and iodine also follow the same thing. Now fluorine shows deviation from this behavior when it reacts with alkali. So like chlorine, bromine and iodine, fluorine doesn't show the similar reaction, it shows a deviation. Now the reaction that takes place in case of fluorine is F2. When it reacts with alkaline medium, it forms F minus ion, OF2 ions and H2O. This is what it forms. So it is to be noted with care that fluorine in reaction will undoubtedly attack water to produce some oxygen also. Here you can say कि fluorine, it will react with oxygen to form some water molecules also. Now this departure shown by fluorine is not surprising for us, as we know that the limitations of fluorine, that being the most electronegative element, it cannot exhibit any positive oxidation state. So it is obvious that it will form a water molecule because fluorine is highly electronegative. So if it doesn't form a water molecule, it will have to face a positive charge on it. So being an electronegative element, it cannot exhibit in a positive oxidation state. So it will form a water molecule. Now this means that among halogens, fluorine does not show a disproportionation tendency. So this reaction also proves that among the other halogen atoms, fluorine is an exception which doesn't show a disproportionation reaction or disproportionation tendency. So here we are done with the types of reaction or types of redox reaction. We have seen disproportionation, we have seen displacement reaction, decomposition, combination reactions. We have also seen about the oxidation number and oxidation state. So thank you for watching my video. Please do like, share and subscribe to our channel.